Hello everyone. Today we're presenting our work on the automated detection and localization of chart patterns using machine learning. Identifying chart patterns is a key skill in financial trading, but it's often a slow and subjective process. Our project uses machine learning to automate this, aiming to make it faster and more reliable. So what's the problem we're trying to solve? Stock charts often form visual patterns that traders use to predict future price movements. However, finding these patterns manually is a slow and skillful process. Different people can interpret the same chart differently, and simple computer rules often fail to adapt to real-world pattern variations. This makes it difficult for traders to spot these important clues quickly and reliably. Our project tackles these challenges head-on. With those problems in mind, our objectives were to, first, overcome the slow, subjective nature of manual analysis. Second, use adaptable, data-driven machine learning instead of rigid rule-based systems. And finally, to rapidly and comprehensively detect and locate a wide range of chart patterns, minimizing missed opportunities. Our methodology began with gathering and preparing the data. We started by sourcing historical chart pattern instances from a well-known resource, bukowskispatternsite.com. Then we acquired the corresponding stock price data using APIs from Yahoo Finance and Investing.com. After cleaning and structuring this data, we focused on 6 specific patterns, including the double top, head and shoulders, and flag patterns. A crucial step here was creating a no pattern category using a technique called positive unlabeled learning, which helps the model distinguish between actual patterns and random market noise. We also enhanced our training data by applying width augmentation, which means we extended the pattern segments to include their surrounding context, helping the model to better locate patterns in a larger chart. The second part of our methodology is the heart of our system, the chart pattern classification model. This model is designed to identify predefined chart patterns within stock price data and assign a probability score to each identification. We took a two-part approach to build this model. First, we used a feature extractor called MiniRocket. This algorithm is incredibly efficient at transforming the time series data into a format that highlights its key shape characteristics. Then we used a classifier called XGBoost to process these features. XGBoost is a powerful machine learning model that classifies the segments into our predefined pattern categories, or as no pattern, and provides a confidence level for each classification. The final part of our methodology is the chart pattern localization algorithm. This is where we take our trained classifier and use it to find and outline patterns in large, continuous stock charts. The process works like this. First, the input chart is scanned with sliding windows of various sizes. Each window is then classified, giving us a probability for each pattern type. Then we filter out any low probability predictions and group together close, similar predictions of the same pattern using a clustering algorithm called dbScan, which also removes outliers. Next, we define the start and end points of the pattern by looking at the intersection of these clustered predictions. And finally, if there are overlapping detections, the system has a smart way of choosing the best one, generally preferring the larger window unless a smaller one has a significantly higher probability score. Now for our evaluation. We tested several classifiers and found that the Rocket family, especially MiniRocket, gave the best speed-accuracy balance for our localization task. However, standard models lacked the probability outputs we needed. This led us to develop our own custom classifier, combining MiniRocket's feature extraction with an XGBoost classifier head, which is powerful and provides those necessary probability scores. Our final classifier, trained with width-augmented data, achieved a test accuracy of 0.731. Interestingly, while other data preparations gave higher standalone accuracy, this width augmentation proved to be the key for superior localization performance, which was our main goal. Our key finding was a trade-off. Our system achieved a high recall, meaning it's great at finding a high percentage of the actual patterns. However, it had low precision, resulting in a high number of false positives, because it also identified many segments that didn't match pre-labeled examples. For the correctly identified patterns, the boundary accuracy showed a reasonable overlap with the true pattern areas. The overall interpretation is that our system's high recall makes it an effective candidate generator, but the low precision means these candidates require further verification. For completeness, we did explore other methods. A baseline GAF-CNN model that encodes time series as images had lower accuracy. Generating synthetic data with TimeGAN was impractical for our patterns, and a custom 1D YOLO V1 model for direct localization performed poorly. Our final Mini-Rocket XGBoost approach proved to be superior to all of these. In conclusion, our project has successfully developed a system that achieves a 0.731 accuracy using a Mini-Rocket XGBoost model. Our key finding is that width augmentation significantly improves the system's recall, making it a valuable tool for initial screening. The main limitation of our current system is its low precision. To address this, our future work will focus on integrating a rule-based filtering layer, improving our data augmentation techniques, and enhancing the features used for classification. We also plan to expand the set of detectable patterns and test our system on more diverse markets. That brings us to the end of our presentation. Thank you for your attention. Now let's go into our demo. This interface is a React application communicating with a Django backend, which hosts our complete machine learning model. When the stock and date range are set, the Django backend calls the Yahoo Finance API for the historical OHLC price data. Now the server is executing the core process. The selected data is being scanned by our Mini-Rocket XGBoost model using multiple window sizes. Simultaneously, the backend is performing DBS scan clustering to group and refine the raw detections before finalizing the pattern boundaries. Finally, the backend sends the refined pattern coordinates and details back to the React app, which then renders the interactive visualizations you see here.